I'm Katharina Rebeck.
And I'm Amy Keating, and it was our pleasure to chair the Program Planning Committee for today's symposium. It's incredibly exciting to see it coming to life. The hardest part of this job, by far, was putting together just a single-day program from the wealth of ideas, innovation that surround us at MIT.
It is, really this wealth of discoveries and innovation that makes MIT so exceptional. Here we're not just exploring new frontiers, we are actively creating them. Now we have the privilege of hearing from four remarkable early career stage faculty who exactly embody this spirit. These rising stars from chemistry, biological engineering, and neuroscience are not only expanding our understanding, they're taking discoveries in bold new directions and really influencing the way we think, the way we innovate, and the way we collaborate.
So Professors Alida Johnson, Brian Bryson, Sarah Prescott, and Sinisha Srivatin will share with you their visions for the future in 4 short talks. Please join us in welcoming them.
Good morning. I am excited to be here today. I'm an assistant professor. This is my 2nd year here at MIT. And my lab is broadly interested in using chemistry to direct protein traffic in cells. Before I tell you what that means, I want to start by asking you a question. What do these 5 people have in common? I'll give you 3 seconds to think about it. All right, if you thought that these people are leaders, innovators, or icons, I'd totally agree with you. As it pertains to my research, they share, unfortunately, another commonality. All 5 of these people were diagnosed with a devastating class of disorders known as neurodegenerative diseases that ultimately robbed them of the physical and cognitive faculties that enabled them to have such a huge impact on the world. With that in mind, I invite you to imagine a world where a diagnosis with one of these diseases is not a timer counting down to some inevitable decline in the way that you engage with those around you. My lab is working right now to turn that world into a reality. And I'll give you an overview of how we plan to do this. But first, I want to be specific about what these 5 different diseases actually have in common. If you look at the photos at the bottom of the slide, these are all photos of tissues from patients that are diagnosed with these diseases. And you'll notice these dark spots that are on the slide in these cells. Those are proteins that are aggregated, a common feature of all 5 diseases. What that means at the molecular level is that proteins that are normally pretty flexible in a cell to do their normal function, they somehow get clumped together in what we call these protein aggregates. We don't always know how they happen or why they happen, but I like to think of some cellular protein highway where one path gets cut off, leading to this cellular protein traffic jam. Similar to if you were to, say, shut down the Sumner Tunnel, and now there's a giant aggregate of cars on the way to the airport. With that in mind, it's important to consider ways to prevent these cellular protein traffic jams from happening in the first place. Luckily, there's a protein that I care about called DNAJB6 that is already very good at directing protein traffic and preventing these aggregates. But as you've seen, it doesn't always work in these diseases. Based on what we know about DNAJB6, my lab has 3 big picture goals. We want to develop new chemical tools that we can use to detect these aggregates earlier than we can right now. We want to learn more about the mechanisms that DNAJB uses to direct protein traffic to see if there's any clues there on what we could do as chemists. And we want to discover chemicals, small molecules, that can work with DNAJB6 to either activate or mimic its activity and prevent aggregates from happening. And I was really lucky to recruit 3 fabulous graduate students in my first year to work on these problems. Cordiana is working on a fluorescence-based platform for early detection of protein aggregates. Aaron is taking really complicated DNA JB6 structures and using chemistry to make them more simple, to make it easier for us to study how they work. And Isha is looking for chemical directors that activate DNA JB6 by acting as glues, recruiting it to a protein of interest in a disease of interest. And that's just the beginning. Because last month I recruited 3 more fantastic graduate students to my group who are going to work on 3 new projects towards our goals. And together, we hope that that will result in better diagnostics and better therapeutics that, had they existed 20 or 30 years ago, would give us more time to learn from the wisdom of experience of people like Rosa Parks, Muhammad Ali, or Stephen Hawking. But most importantly, we hope that the tools that we develop in my lab could be used to improve the quality of life for people who are diagnosed with these diseases, ordinary, everyday people like you and like me. Thank you.
Good morning, everyone. I'd like us to imagine a world without tuberculosis. This is the Granville mummy, estimated to be found in 600 BC. At the time when they unearthed this mummy, they thought that the cause of death for this mummy was ovarian cancer. However, in the early 2000s, researchers found that this mummy had had tuberculosis. Fast forward to the 19th century, where it's estimated that 1 in 7 individuals was dying from tuberculosis. This is an ad from the Christmas Seals asking you to donate money to stamp out tuberculosis. But unfortunately, I'm here to report that the Christmas Seals were unsuccessful in this campaign because today alone, 4,000 people will die from TB. Okay, so what would be transformative? What would be transformative for TB is a protective vaccine, and this is something that we do not yet have. We have one vaccine for TB. It is over 100 years old, and it doesn't meet the product profile needed to end this pandemic. However, if we did, it would change history. So looking at this graph, this is TB incidence per million on the y-axis and time on the x-axis. If we do nothing and we just keep standard of care, that's the red line. If we had a 60% protective vaccine and a mass vaccination campaign, look at what could happen. All right, so the question becomes, how do we get there? How do we make a protective TB vaccine? All right, so that's the question that my lab decided to tackle. So why aren't we there yet? We heard about measurement. I would like to submit to you that this is a measurement problem. Okay, so the question becomes, how do you design a vaccine in the first place? We might all be experts about designing vaccines for viral pathogens, but tuberculosis is caused by a bacterium. So when I think about this problem as an engineer, I think about the following question. What proteins from the bacterium does the immune system see? All right. This is an especially hard problem in the context of infection with bacteria because viruses have tens of proteins. TB has 4,000, right? So it's not that simple just to say, which protein do I pick? It's actually a really hard problem. And to make that problem even just a smidge more difficult, we have to do this in a biosafety level 3 environment, which means that everything just goes much slower, much more complicated, and much more arduous because this isn't some place where you can just say, I want to try something new and do it tomorrow. This takes a lot of effort and energy. So despite those roadblocks, I'm really excited to share with you that we've made significant inroads to this problem. Okay, so how do we do this? So work led by an incredibly talented graduate student in collaboration with Forrest White, we set out to address the measurement problem, asking specifically in human cells across diverse human genotypes, if we infect with TB, what proteins from the bacterium are seen by the immune system? So I'm going to call this problem solved. We can do it within days now. Okay, so now the next question becomes, if you can make these measurements and ask what the immune system sees with bacteria, can we ask, what does the immune system see when you give a vaccine, including those proteins from the bacterium? And that's what we've been able to do now. So now we can design vaccines as mRNAs and within weeks get an answer about a particular design that we've made. And to give you an example of what we've done just in the last few years is we've made all these different vaccine prototypes. And I don't have the time to go through all the details, but what we can do now with these measurement technologies and say, what if we change just one parameter about this mRNA vaccine? How does it change immune output? So that's what you're looking at here on the right graph, where I'm just showing two vaccine designs, where we just made a small 100 amino acid change to the mRNA vaccine, and we can change immune output by orders of magnitude. So while this has seemed like a millennia-old problem for a very long time, I'm very optimistic. I'm incredibly optimistic because I think we can do this. So I'll leave you with a provocative question, which is, will the next TB vaccine come from Kendall Square? And I think it will. I'm very encouraged by this because in the last 6 years, I think we've done so much to answer really a millennia-old problem, but I think we can do so much more, and I think the momentum is on our side. Thank you.
Imagine a world where we understood how our daily stress was damaging our health. We could track it with simple tests and intervene to prevent or reverse its harmful effects. In this world, stress would no longer silently fuel chronic disease, wreak havoc on our mental health, and reinforce social inequities. We all face stress in daily life, but globally, stress levels are now at an all-time high. This Gallup poll asked people around the world to self-report their daily stress levels as part of a negative experience index. And for over a decade, stress levels have been consistently rising, driven by factors like financial insecurity, social isolation, and workplace burnout. These same studies show that stress levels are unequally distributed across different countries and demographics. Within the US, stress levels are highest in college-age adolescents, in women, and low-income and minority groups. Looking at these statistics, it's hard not to feel that we are living in a pandemic of stress, with marginalized communities and our youth, the very future of our nation, bearing the heaviest burden. The consequences of this on society are massive, damaging not just our mental health, but our physical health as well. Children, for example, who experience severe early life stress, as measured by high ACE scores, lose over a decade of life expectancy and are at higher risk for conditions like cardiovascular disease, infertility, and cancer. This association between stress and worse health outcomes is also seen in animal models. For example, early life stress reduces survival in wild baboons and causes mice that are raised in lab environments to develop predictable pathologies, like making their very hair turn gray. These observations tell us that these associations between stress and worse health outcomes cannot be explained entirely by diet, smoking, and access to healthcare services. And it begs the question of what biological processes link stress to increased disease and mortality risk. I'm a neuroscientist, and my lab studies how the brain controls essential functions like breathing and heart rate. And we see stress not just as a feeling, but as a biological program with specific purpose and patterns. When we face a threat, the brain primes the body for action by triggering the sympathetic nervous system to release norepinephrine, causing rapid breathing, a racing heart, and sweating. These circuits also signal endocrine centers like the adrenal glands to produce cortisol and other hormones, keeping the body on high alert. Cells throughout the body receive these signals and are forever changed. With new tools, we can now monitor and target these pathways with unprecedented precision to ask which precise circuits are disrupted by chronic and severe stress. How do stress signals affect different cell types throughout the body? And how are these changes remembered at the molecular scale? Through this lens, we can view stress as a predictable program that can be tracked and treated. To understand this, we're collaborating with other Boston area labs, using animal models to control stress exposures, and then using advanced imaging and molecular tools to track within individual animals how this rewires brain activity and disrupts physiological systems. These comprehensive data sets capture a more holistic view of stress and are helping us predict causal brain changes that alter bodily states and lead to stress-related disease. Looking ahead, addressing this health crisis requires new perspectives and solutions. As for cancer research, we must both learn core principles while also embracing stress's complexity and endotypes if we want to advance precision treatments. This effort will rest on pillars of collaboration across disciplines to better understand the molecular scars of stress and to build evidence-based diagnostics and interventions within our community. And I, for one, am looking forward to this bright future. Thank you all for your attention.
Good morning. My name is Sini Shakharbatin. I'm honored to be here. I want you this morning to imagine a world in which suspended animation were possible. A world in which a 10-year-old girl suffering an incurable disease like maybe glioblastoma, instead of imminently dying, has a choice to enter a state of suspended animation for a few years, maybe a decade, and then wake up at a time in which there is a treatment or perhaps even a cure to that disease. I know this is currently science fiction, pretty much complete science fiction. But what I want to share with you today is that there are animals in nature that have the ability to enter similar states and that have the ability to enter something like suspended animation that I think we can learn so much from and then learn how to eventually develop suspended animation for humans. So I'll share with you examples of a few of these animals. This is the Arctic ground squirrel. This animal lives above the Arctic Circle at very low temperatures. And during most of the year, it has a normal body temperature just like you and me, around 37 degrees Celsius. But during the winter, it can survive by entering hibernation. And it can lower its body temperature all the way down to around 0 degrees Celsius, entering a sleep-like state that we call torpor. My laboratory studies how animals enter torpor and also how do their cells survive at these very low temperatures. And I want to share with you a couple of things that we've recently found. We identified a population of neurons in the brain that controls torpor. And remarkably, we can actually initiate a torpor-like state, even in animals that don't naturally hibernate, just by stimulating these neurons. So here you can see an example of a laboratory mouse. This is a thermal camera image. It has a body temperature around 37 degrees Celsius. But when you stimulate these neurons, you can lower the body temperature of this animal all the way down to around 25 degrees Celsius. Now, this is not as low as a natural hibernator, but it's actually really cold for a mouse. And we can do this not only for minutes or hours, but actually for days to weeks, showing for the first time that we can induce a long-term torpor-like state in an animal that doesn't naturally hibernate. We've also, in a parallel study, started looking at how do hibernator cells survive at these low temperatures and seeing whether we can learn from their mechanisms to improve human cell cold survival. And here you can see an example of a handful of human cell lines that don't fare very well at 4 degrees Celsius. But then when we take small molecules that mimic some of the adaptations that hibernators have during hibernation and treat those cells with them, we can dramatically improve their cold tolerance. And you can immediately imagine how this could be useful for organ storage or organ transplantation, and also how eventually we could use this to learn how to lower the temperature of the human body to lower and lower temperatures. And finally, perhaps the greatest example of suspended animation in nature are these tardigrades, cute little organisms that actually live all over our globe, from the Arctic to the Antarctic. And they have an incredible ability to survive being frozen all the way down to negative 150 degrees Celsius. And they can stay in that state for months to years and then come out of it essentially unharmed. We're trying to understand how tardigrades survive this and whether we can transfer some of those adaptations to human cells. Now, life on Earth has evolved incredible adaptations to survive in extreme environments, and I believe that by studying these animals, we'll learn to harness some of the mechanisms behind these adaptations to advanced medicine, perhaps even one day open the door to fantastic possibilities of space travel. Now, this work needs to start with fundamental biological discoveries, but in order to develop this as a technology, we also need to collaborate with engineers, chemists, physicists, physicians, and this is precisely why there is no place like MIT to pursue this dream. Thank you.